हेलो स्टूडेंट्स, आज हम कुछ डेफिनेशन करेंगे और एक बड़ा ही इम्पोर्टेंट रिजल्ट करेंगे Cauchy's सीक्वेंस से रिलेटेड. So let us start with the first definition, that is limit point. In fact, we have already done this definition in previous chapters, but we will revise this definition because this is the important part. We will use the concept of limit point and cluster point. A point, if you remember, a point, any point is a limit point of a set. We have discussed it in bounded sets. So, but now we are discussing this limit point as a limit point of sequence. So instead of set, we will talk about sequence. So a limit point, any point is said to be a limit point of a sequence if in each neighborhood of that point there are infinite number of terms of that sequence. That is, how can we write in mathematical form? That is, a real number L is said to be a limit point of sequence xn if for each epsilon greater than 0, xn belongs to L minus epsilon comma L plus epsilon for infinitely many n, right? For infinitely many n, where n belongs to natural numbers. The meaning of this is just that any point is said to be a limit point if it contains infinite number of terms in its this interval, infinite number of sequence in this interval, right? For example, if I take xn equals to 1 by n, then obviously 0 is the limit point of xn. One thing I want to make you clear, that we are talking about number of terms. We are not talking about elements or numbers around L. For example, if I take xn equals to minus 1 raised to power n, then you can see there will be no element around these, no real number of this sequence which lie in the neighborhood of minus 1, and there is no real number in the neighborhood of 1 also. But we are talking about terms of the sequence, right? So that point is a limit point in which each neighborhood contains infinite terms of sequence. Infinite terms, हम terms की बात कर रहे हैं, हम number की बात नहीं कर रहे हैं. अब यहाँ पे 1 और -1 is the limit point. इसको थोड़ा ध्यान से समझो, limit point of xn. अब आप देखोगे कि 1 और -1 के आसपास तो कोई भी नंबर नहीं है सीक्वेंस का, राइट? बट जब हम इस डेफिनेशन को देखेंगे तो हमें यहाँ से पता चलता है कि वी आर टॉकिंग अबाउट टर्म्स. हम सीक्वेंस की टर्म्स को देख रहे हैं. अब अगर मैं देखूं कि -1 के आसपास कितनी टर्म्स हैं, आप देखोगे जितनी भी और टर्म्स हैं वो सारी इसी नेबरहुड में -1 है, वो सारी की सारी. अब कितनी ऑड टर्म्स हैं, देयर आर इनफाइनाइट ऑड टर्म्स. सो सारी की सारी इनफाइनाइट ऑड टर्म्स जो है वो -1 ही है. तो मैं इसका कोई भी नेबरहुड ले लूँगा, बड़े से बड़े छोटे से छोटा, वो सब उस सभी नेबरहुड्स में इनफाइनाइट टर्म्स जो हैं वो लाई करेंगी. सो -1 हमारा लिमिट पॉइंट हो गया xn का। इसी तरह जितनी भी इवन टर्म्स हैं वो सारी 1 है, राइट। सो यहाँ पे x2 भी है, x4 भी है, x6 भी है एंड सो ऑन, सारी की सारी टर्म्स कहाँ है, यहाँ पे 1 पे, राइट। सो 1 पे कौन कौन सी टर्म है, x2, x4, x6 एंड सो ऑन। सो देयर आर इन्फिनिट टर्म्स ऑन 1, राइट। सो इफ आई टेक एनी नेबरहुड ऑफ 1, छोटे से छोटा बड़े से बड़ा, जितना मर्जी मैं नेबरहुड कोई भी ले लूँ, जितना मर्जी छोटा एप्सिलॉन ले लूँ, जितना मर्जी बड़ा एप्सिलॉन ले लूँ, तो मेरे पास जो है वो सीक्वेंस की इनफाइनाइट टर्म्स आएंगी इस नेबरहुड में। क्यों, वो सारी की सारी जो है वो इवन है। और यहाँ पे हमारी कौन सी आ रही है, ऑड टर्म्स, मीन्स x1, x3, x5 एंड सो ऑन। तो ये सारी टर्म्स हमारी यहाँ पे आ रही है, इसलिए 1 और -1 जो है वो दोनों के दोनों लिमिट पॉइंट होंगे एक्सन के, राइट। सो आई होप ये आइडिया आपको क्लियर हो गया होगा कि लिमिट पॉइंट ऑफ सीक्वेंस का क्या मतलब होता है, ठीक है। सो लेट अस मूव फॉरवर्ड। देयर इज एन इम्पॉर्टेंट स्टेटमेंट which is called Bolzano-Weierstrass theorem. We have only statement and the proof of this theorem is beyond our syllabus, so we will not discuss the proof, but I will discuss this statement only. Just to discuss this statement I have explained this definition again. So the statement is very important. Every bounded sequence has a limit point, you can see above. These two examples are the examples of bounded sequence only, and first case we have only one limit point, and in second case we have two limit points. So every bounded sequence has a limit point, at least one तो होगा ही, उससे ज़्यादा भी हो सकते हैं, right. So this was the important result. और नेक्स्ट जो इम्पोर्टेंट रिजल्ट है वो हमारा कोशी सीक्वेंस से रिलेटेड, जो हम पिछले वीडियो में जो हमने डेफिनेशन की है उसी से रिलेटेड बहुत ही इम्पोर्टेंट एक रिजल्ट है, आर्टिकल है, और इसको हम आर्टिकल को बोलते हैं कोशीज जनरल प्रिंसिपल ऑफ कन्वर्जेंस। Cauchy's general principle of convergence, right. So statement क्या है, a sequence of real numbers converges if and only if it is a Cauchy sequence, right. So very important proof, very important result. I am again repeating this statement. A sequence of real number converges if and only if it is a Cauchy sequence. Now statement is if and only if, that means it is true both sides. Means if sequence converges then it is Cauchy sequence, and converse is also true, that is if sequence is a Cauchy sequence then it is convergent. So first we will take that sequence is a convergent sequence and we will prove that it is also a Cauchy sequence, right. So let us start the definition, the proof. Consider a sequence xn which converges to L, right. That is xn is converging to L. So by definition of convergence, for each given epsilon greater than 0 there exists n natural number such that xn minus L is less than epsilon by 2. for all n greater than equal to capital N. So I have written here epsilon by 2. I have already explained it in detail that why we write some other real number instead of epsilon. So I am removing this 2 and I will write it again whenever I will feel like to write it, right? So जब भी मुझे लगेगा कि मैं इसको epsilon by 2 कर दूँ तो मैं इसको epsilon by 2 कर दूँगा, है ना? So इसको याद करने की ज़रूरत नहीं है. You don't need to cram it that we should write what should be written here. So let us move forward. So xn minus L is less than epsilon for all n greater than equal to n. Let this statement be statement 1. So now we want to prove that any two we have to find a stage, and after that stage any two terms of sequence, the difference of any two terms of sequence should be less than epsilon. So I am taking xn and xm, right, and I am subtracting and adding L in this xm minus xm. This can be less than equal to xn minus L plus xm minus L, right? So now this will be less than equal to epsilon plus epsilon for all n comma m greater than equal to capital N, because सभी n जो n से बड़े हो, कैपिटल n से बड़े हो, उनके लिए ये कंडीशन होल्ड करेगी. Now I want epsilon, so I will divide it by 2. So here I will again use epsilon by 2. So अगर ये xn minus L लेस देन एप्सिलॉन बाय 2 कब होगा? जब n जो है वो ग्रेटर देन n चाहिए. सिमिलरली xm minus L वो लेस देन एप्सिलॉन बाय 2 कब होगा? when m is greater than equal to n. So I have written here nm greater than equal to n. So xn minus xm is less than epsilon for all n comma m greater than equal to capital N, right? So this implies, इसका मतलब क्या हुआ? This implies xn is a Cauchy sequence. हमें एक ऐसी स्टेज मिल गई जिसके बाद वाली टर्म जो है वो उनका डिफरेंस लेस देन एप्सिलॉन है. सो दिस वाज एन इजी प्रूफ. सो नाउ वी विल प्रूफ इट, वी विल प्रूव द कन्वर्स ऑफ दिस रिजल्ट, राइट? So let us start the converse of this proof. Converse is, if a sequence is Cauchy sequence, then it is convergent. So let us take a Cauchy sequence. Let xn be a Cauchy sequence. Since every Cauchy sequence is bounded by we have already proved that every Cauchy sequence is bounded sequence. So xn is bounded sequence, and by Bolzano-Weierstrass theorem, each bounded sequence has a limit point. So therefore xn has a limit point, right? So by, we can write here by Bolzano-Weierstrass theorem. Sorry, let L be the limit point of xn. Then for each epsilon greater than 0, xn belongs to L minus epsilon comma L plus epsilon for infinitely many terms, many n. Yes, right? So for fixed epsilon, for this epsilon, for given epsilon, now since this sequence is also a Cauchy sequence, so the sequence by definition of Cauchy sequence for this given epsilon, which we have considered here in as by taking a limit point. So for this same epsilon we can find a stage. There exists a natural number n belongs such that xn minus xn is less than epsilon for all n greater than equal to capital N. So here we have taken epsilon, here we have again taken epsilon. Now we will prove that this sequence xn is convergent and it will converge to L, the limit point, right, by using these two statements. First one is this and second one is this. So we will use these statements in order to prove that xn is converging to L. Now how can so if we want to prove that xn is converging to L, so we want to find a stage n such that xn minus L is less than epsilon for all n greater than equal to n. So I am considering this xn minus L, and I can take particular xn which lies after that n. So before using this, so from 1 we take k belongs to natural number such that k is greater than equal to n and xk belongs to L minus epsilon comma L plus epsilon, right? So because there are infinitely many terms which lies between L minus epsilon and L plus epsilon, so I have taken particularly those xk which are greater than n, right, so that these xk belongs to 1 and 2 simultaneously, right? So consider, now we are considering the xn minus L terms, L mod. So I will add some values like minus xn plus xn minus xk plus xk minus L, and this will be less than equal to xn minus xn plus xn minus xk plus xk minus L, right? Now clearly, what is the meaning of this statement? This statement only means that xn minus L is less than epsilon for infinitely many terms. Right. So now this implies this is epsilon. So xn minus xn, this is same by using 2 plus xn minus xk, where k is also greater than equal to n, so this again comes from the statement 2 and it will give us epsilon, and xk minus L also holds for this, right? It belongs to L minus epsilon to L plus epsilon, so by using 1 we can write it as epsilon, but we have 3 epsilons, so the answer will be 3 epsilon. So in order to make it epsilon, we will divide it by 3. So we will change all epsilon by 3. So I will replace all epsilon with epsilon by 3. So this gives us, so this holds only for all n greater than equal to capital N. Not for this, but for last statement. Here I have not put any condition, but here I have used only those n which are greater than equal to n. So this equals to epsilon. So therefore, finally, what we get xn minus L is less than epsilon for all n greater than equal to n. That is, xn is converging to L. Hence, every Cauchy sequence is convergent. So in this particular proof, we use the definition of bounded sequence, we use the definition of limit point, cluster point of a sequence, and we also use the result of Bolzano-Weierstrass theorem. So that is why we discussed previously, I discussed these two concepts. One is definition of limit point, cluster point of sequence, and second is Bolzano-Weierstrass theorem, because I need these two definitions to prove the converse of this theorem. So I hope the ideas, the concept is clear to you. Please go through this proof again and again so that you can have a better idea. So that is for all. That is all for now. I will post the next video very soon. Thank you.